going to take you to a different world, where I suspect actually the complexity is rather similar. The budgets are absolutely minuscule. It may be a BIM-free area for a time. I don't know. We'll see. Looking at the challenge of how we retrofit the existing building stock in this country to deal with two aspects of climate change. So I'm not going to talk a lot about BIM, but there'll be some references to it. So they're basically, going back to the beginning, they're basically sort of two challenges to deal with climate change. One is mitigation, which is reducing emissions so that we don't damage the climate as much as we are currently doing so. And then the other is adaptation, which is recognising that the climate is changing, has changed, will change, and designing for a different climate, which is something that we've never done before. And we have to do it using modelling. And there's some things that you can do in design that deal with both agendas. An example of that would be using sort of low energy lighting or low energy equipment. You save money, you reduce carbon emissions, you reduce the heat inputs to buildings, and therefore you reduce the cooling load. So it's a win-win situation. But there are things where you try and solve one problem and you cause another. And one of the examples I've used for that would be we did an awful lot of schools fairly recently. You've got lots of BREEAM points, for including good daylighting. And what people tended to forget was that daylighting, if it's not controlled, introduces solar gain to buildings, so you end up actually creating a problem. You're solving a lighting problem, maybe, but in fact, when you get glare and solar gain, people draw the blinds so the lights are running on anyway, so you undersave that, and you're then adding heat into the building, you're then creating a cooling load, you have to add cooling. So you're trying to solve one problem, and the unforeseen consequences, you actually create another problem and actually go backwards in solving the first problem. So I'm sure you're aware of the climate change headlines of the UK: hotter, drier summers, warmer winters, more extreme events and sea level rise. Just to sort of illustrate the issue, climate scientists hate these sorts of analyses, but I find them useful. You can say that the summertime temperatures of London in 2080 will be similar to those from Marseille today, just to give you a handle on the amount of change we might be looking at. So that's a street in London, a very patriotic street, which is broad to let daylight into our buildings in our miserable grey climate that we live in. And that's the street in Marseille. You can see this is a very different built form. The streets are narrow, the buildings have heavyweight buildings, shutters to keep the sun out, etc. And what I guess we're beginning to realise is that built form and construction and lifestyle have all go together over millennia to create places where life, buildings, cities are all integrated. So, for example, the siesta in Marseille is a way of avoiding trying to work in the hot parts of the day. You basically go home, have a snooze, come back when it's cooler and you can work. The consequence of that is that probably the people are more interesting, the food's better, but also people tend to live and work closer together. What we're faced with is trying to convert a built environment built in one climate to another climate, and nobody's done that before. So I live in Bath, people commute from Bath to London. You can't nip home for lunch and a siesta, so these options aren't available to you unless you have siesta hotels with unbelievable consequences for the office of that. Some things don't change, however. So that's the midday summer sun angle in Marseille, and that's the midday summer sun angle in London. So you cannot lift sort of climate solutions from one environment and dump them in another. We actually have to think from first principles to reconsider the way we design buildings. And the other crucial point to note, we always talk about new build, and a lot of the discussion today will be about new buildings, where everything fits beautifully. This is a conversion job. We're converting built environments, including the buildings that make them up, for different climates, as I say, no one's done that before. And just to illustrate the point, again, you're probably aware of this statistic, that 80% of the homes standard in 2050 exist today. So it's a conversion job. We can't build our way out of this. In fact, building new homes tends to make it worse. There's lots of climate information available in the UK. The UK's CP09 website contains huge amounts of climate information, but it's used as a probabilist approach, which I won't describe, but it adds complexity, need translating into forms that we can actually use for building design. There's some very good examples of how that information has been translated, and also lots of examples where it hasn't been translated. There's also gaps in the information, particularly around wind, for example. I won't get into why that is, but it means that we don't necessarily have complete information about future climates to deal with something, with essential issues on construction. So I wrote a short guide for a technology strategy boards for Innovate UK program a few years ago called Design for Climate, which tried to sort of set out the issues facing the industry, and I broke the issues down into 3 very simple factors. Comfort, which is predominantly just keeping cool in the summer. Construction, bits falling off buildings with changing climate, how materials change, the way they actually work, which I'll talk about a bit more later. And water, too much and too little, fundamentally. Flooding and drought. There's a context in which we have to think about solutions for adapted buildings. First is that there's no climate change is a regional issue, and you won't be thinking necessarily about the same things in one place as you are in another. So in the southeast, you might be particularly interested in overheating. The hottest part of the country is going to change fastest. I live up a hill in Bath. I'm not particularly interested in flooding, but if you're living in Hull or somewhere like that, you are very interested. So the issues at which you will be really focusing on will vary according to where you are, both geographically and also in terms of sort of local features. The existing stock is the key issue, as I said before, and you can't simply just throw energy, which normally means throw carbon, at problems. So the fact that we may get warm in summer, it doesn't mean we can just install air conditioning in all our homes, because the future will be, we're trying not to emit carbon, and energy, I suspect, will be scarcer and more expensive in the future. So it's not sensible to simply throw energy at a problem. There are various tactics you can use. One is timing, because climate change is a moving target, so there's no such thing as a climate-proof building. People tend to sort of throw that term around, which is clearly nonsense. I don't know how far the climate is going to change. But there are some things you want to get absolutely right when you're designing a new building, like foundations. You don't want to be digging out the building for a few years down the line. But things like windows are actually rather temporary affairs. They might last 20 years, 25 years. And so you've got opportunities as you go through the life of a building to add elements and alter elements that change the fundamental performance of those buildings over time. So for those elements, all you need to do is to think about the lifetime of that element. And then scale. There's a tendency amongst designers to try to solve all problems within their project. And actually, sometimes it's better to solve them at a different scale. The example I tend to give for that is, again, you used to get lots of points for installing rainwater harvesting tanks in housing. Quite often these were small tanks, quite a lot of embodied carbon, quite often not commissioned properly, so it may not have worked ever. Quite a lot of them won't be working now. Again, so you're trying to solve a problem, you're going backwards in terms of the embodied energy, and it may not actually be a long-term solution. Maintaining the equipment in the domestic environment is very tricky. Actually, it's probably better to build a reservoir. So in terms of a society, we need to decide at what scale we try to solve these problems. The basic challenge ahead of us, though, in altering, in retrofitting the existing stock, in terms of mitigation agenda, is to reduce our total emissions by 80%. And I always do it graphically because it makes you realise how, what a challenge that is. And most of the time we talk about making microscopic changes, sort of fiddling at the edges, and actually the challenge ahead of us is very, very significant. And there's another Technology Strategy Board project called Retrofit for the Future that tried to look at what it would be like to reduce the emissions, the energy consumption, or carbon emissions, almost synonymous with that energy consumption, of existing housing by 80%. So I think there were about 100 projects which all got about £100,000 each. It's a very large amount of money for an individual little house to look at how you would reduce their energy consumption by 80%, by carbon emissions by 80%. And it's, the standard is approaching passive house. So it's actually trying to make existing homes better than the homes we are currently building. It seems slightly topsy-turvy, but that was the challenge. And the techniques you have available to you, obviously you can improve insulation, roofs, walls, floors, etc. You can improve the windows, change the windows, triple glazing. That's the level you have to go to achieve these sorts of targets. Crucially, improve air tightness to get it down to very low levels of air tightness, down to passive house levels of air tightness, which means introducing ventilation systems. Obviously, upgrading services so they're more efficient. Incorporating renewables where they're appropriate, and also looking at how behaviour influences, how the behaviour of the occupants can influence the energy consumption of the buildings. Now, all of these things are difficult to do. So some of the lessons learned from this project is that it's not easy. And as I was saying, I quipped at the beginning, that the number of decisions you have to make and the complexity of the installation for a small terrace house in Manchester, I suspect is not far different from a weekend's work, network work. In terms of sequencing of trades, of actions, it's actually an extraordinarily complicated process. Also, you can design things in theory, but theory and practice are never the same. So even when you design a very low energy building in theory, in practice there are all sorts of reasons why it doesn't perform properly. I won't go into them, but they have to be designed right. Working with existing buildings is a nightmare because things are never in the place you thought they were going to be. Everything's bent. BIM seems to exist in a world where everything's straight and shiny. So that's not the world of existing buildings. Although people were using laser cloud scanning to measure for insulation, for example. There's quite innovative ideas using some of the techniques that we've been talking about today, which were helpful. Dealing with existing fabric, trying to find a route for a duct through a large duct through existing fabric is very difficult. Knowing where the fabric is, what walls are made up, how walls are made up before you have pulled them down. It's sort of forensic examination, investigation. Obviously, limitations on space. The amount of insulation you're having to put into a building is something getting on for 200 millimetres of mineral fibre. So if you've got a small bathroom in the back of your house and you start internally insulating with that, the bathroom has disappeared by the time you do it. Installing unfamiliar technologies, unfamiliar both to the designers and also to the occupants. So making sure that everything works and people understand new technologies is a real challenge. And people tend to blame, people like me, tend to blame the occupants when they need training. Well, actually, it's probably the designers who need training to the real occupants. It's a two-way process of understanding how things work significantly. So that's all about people. And quite often the people remained in these buildings while they were being gutted and stripped out. So it's a very stressful, disruptive process. But this is the challenge we're faced with. And can BIM help in this world? But one of the big issues that emerged, I think principally from this work, was looking at how moisture moves through, particularly through solid wall constructions in a way that we haven't fully appreciated. So that's the makeup of the existing stock by age. So it's principally those buildings, 20% of our stock that is solid wall buildings. And solid wall buildings behave, as we now sort of discover, in a very different way from cavity wall buildings. And moisture is, the way moisture moves through those walls is very, very well, counterintuitive to someone brought up on vapor barriers and those sorts of things. So, there are three ways moisture moves through a solid wall, and this is work by Joseph Little, who's been very helpful in developing this work. And this is the way we traditionally think. In a dry wall, the principal moisture driver is vapor diffusion from the inside out. So we're terrified in buildings of warm, moist air getting into walls and condensing out. But in winter, the moisture movement tends to be in the other direction. It's basically rain falling on an external wall, on a brick wall, and gradually finding its way through to the inside surface of a wall. And in some cases, you can have moisture moving in both directions at the same time through different mechanisms. I think this is something we haven't registered. And in order to understand this sort of, these sorts of moisture movements, you need to know an awful lot about the materials that make up the wall. And of course, materials in a conventional solid wall are a complete mess and a muddle. It's mortar and bricks the bricks vary. I did some work for Trinity College, Cambridge, which you'd have thought would be built properly in the 19th century. And we actually analysed some of the bricks. Normally you have to take the material definitions from the library. We actually analysed the bricks, and we took half a dozen bricks for an analysis, and they were all wildly different. So trying to, the science requires rather more precision than reality offers. So we use things like Woofy, or Woofy, it's a German software analytical tool that looks at thermal and moisture movements through walls over time. So looking at how walls dry out in the summer and get wetter in the winter. And one of the things that emerges is that when you start to insulate internally on a solid wall, the moisture content of the wall goes up. You can imagine that the heat from the inside the building is not going into the wall and driving the moisture out, so the wall gets cooler and wetter. And it varies, the more you insulate, the more of a problem that is. So one building, more insulation means more care. Also, location is incredibly important. So these are similar facing walls, southwest facing walls in these different locations, Swansea, Liverpool, Manchester and London. And you can see there's a very wide variation between those locations, and that's all to do with rainfall and exposure in those places. The other thing is that the direction of wall faces also has a very significant effect. So a north-facing wall in Swansea is equivalent to a southwest-facing wall in London. So to do this sort of analysis, it requires a very high degree of understanding and data to enable you to do it. Now, if the wonderful world of BIM could allow us quickly and easily, to just analyse walls on the basis of a model, but I think the word "just" is always very, very dangerous in this sort of world, because the amount of effort to convert BIM models to useful models that can be interpreted by other pieces of software is pretty significant and error-prone. So one of the things that came out of this work was that the project had been looking to achieve passive house standards, which requires a wall U value of the thermal performance of a wall below 0.15 watts per square metre per degree Kelvin. And the Passive House Institute have, almost simultaneously with this work, produced a retrofit standard, NFIT standard, which recognises that it's actually dangerous to try to insulate to that level. And their standard for retrofit is now 0.35, very much higher. Lower thermal performance. And that's to help reduce problems of extreme amounts of insulation. And then if you add climate change to this, what happens? Warmer, wetter winters, the pattern of rainfall changes. So what happens? Now this is my own analysis, which is deeply unscientific, but I think it hopefully gets the price for the concept across. So this is the wind-driven rain map of the UK. So blue is lots of wind and wet, and white is not too much. And those places, London, Manchester, Liverpool, and Swansea, are there. So you can see that's the rainfall, winter rainfall across the UK. And you can see it rains a lot. It rains quite a lot in Manchester, a heck of a lot in Swansea, not much in London. So those are the amounts of rainfall in those locations. And you can see there's actually about 100% difference between the rainfall in Swansea and London. So it's very, very significant. What happens by 2050? Not a lot in terms of rainfall. So there's a small change in rainfall for, say, Swansea, the worst case. By 2080, there's a bit more, so that Manchester is approaching the rainfall conditions of Swansea today. So obviously, these are the sorts of things. It's not terminal, but these are the sorts of things that need to be thought about when you're designing an internal insulation system. And I didn't time terribly. Okay, right. But one of the things we haven't sort of realised, going back to the trying to solve one problem and creating another, is how the way we change buildings, and retrofitting is changing a building in retrospect, but we also have changed the way we build over the past few years. If you look at this balancing act of maintaining comfort by the fabric of the building, you have losses, conduction losses through the walls, you have ventilation losses. We used to heat up air and then throw it out of the window in winter, and we do that in our existing buildings very convincingly. You balance that against heat gains from people, equipment, lighting. These arrows are, roughly speaking, the right sort of size in terms of quantum. There's a bit of solar gain in our miserable country. And so we need quite big heating systems. It's a heating problem, and we have a heating season from September to April or so. If you retrofit a building, or change the building standards, the ventilation losses are cut very, very significantly. The conduction losses are cut very, very significantly. And that means we don't need much heating, so the hot water load dominates rather than the space heating. And that shortens the heating season by about 4 months. And so what we haven't registered is the rest of the year we're trying to lose heat rather than gain heat. So one of the things that we haven't thought about too much in terms of strategy is what happens in summer. So in summer the conduction losses go down, the solar gain goes up, the sun comes out, and so what do? It's out of balance. You might consider adding active cooling. There is now a growing trend, particularly in London, to add active cooling. And that gives you a license to do stupid things, so I think that it's a bad idea, and obviously going backwards in terms of carbon emissions. So what do? As a designer, you obviously minimise lighting and equipment loads, makes sense. Think about the number of people, because actually you need to allow for rather more people than standard, probably in terms of safety, in terms of resilience. Solar gain is an absolutely crucial tool to shade windows so that you don't emit too much solar gain. And ventilation is the other tool, and lots of ventilation is required. We're not very good at designing ventilation at homes, and when we're retrofitting buildings, we tend to seal them up. And concentrating on doing that, we forget that we actually have to open the windows in summer. So there are quite a lot of examples of retrofitted buildings that actually overheat in summer as an unforeseen consequence. Existing buildings have quite a lot of fabric storage, so thermal mass. So heat is stored in the materials and can even out temperatures between day and night. But if you don't ventilate that heat away at the end of the day, thermal mass is a pain in the neck rather than an asset. The building just heats up. So coupling secure nighttime ventilation with thermal mass is very, very important. And again, something we haven't quite registered. And then you add climate change into this equation, and that's pushing the balance point over. So more and more we have to be thinking about keeping cool in summer. So analysing that requires dynamic simulation. Obviously, potential links to BIM, although what I was saying previously about how you transfer information between different modeling environments is interesting. But it's using modelling as a design tool rather than verifying in retrospect what your design decisions. So in terms of what we need to do as building professionals, I'm an architect. Clearly you need to understand the issue because we are designing buildings in an environment. If the environment is changing, we need to understand that and respond to it, or decide whether we respond to it. Discuss this with the client, because at the moment it's very vague about what one's supposed to do. If the client says I'm not interested, well, if the client says I am interested, you need to define what climate variables you are designing to, because as I said, there's no such thing as a climate-proof building. So deciding when you're picking a climate to design to. If the client says they are not interested, that is not an excuse for a free rein of designing stupid things, penthouses with too much glass, with no insulation on the roof, and having air conditioning. It's a silly thing to do, and people are actually being sued in America for doing things like that, which I won't go into. So just to finish with those excellent books and pieces of information, which you can get more information on this, and thank you very much.
Ladies and gentlemen, I'm not technically minded. I'm old school. When IT people actually come to me, start talking to me in IT speak, my question is, just tell me which button to press. So I'm going to do this talk about how CDM potentially, and health and safety in general, can be incorporated into the BIM process, and where there are synergies between what health and safety and the CDM regulations require and what is provided by the BIM process. So that's fundamentally where I'm going from on this, and hopefully it will work. So I'm not sure if any of you are aware of the CDM regulations, Construction Design and Management Regulations, only piece of health and safety law that's specific to the construction industry and requires certain things to be put into place. But what it's about, the clue is in the title. It's about design and management and construction. So it shouldn't be too surprising as to what it actually requires us to do. But what it does require us to do, in broad terms, is coordinate everything that we're doing on a construction project, that all people involved in the project have to cooperate, and to enable everything to work swimmingly, communicate. It's obviously got the health and safety hat onto it, so because it's health and safety law, but I would suggest that sounds a bit like management. It also sounds a bit like what BIM requires. So there is quite a lot of synergy between these. And one of the previous presenters actually stole my thunder on this one. Because basically, he was talking about BIM, was getting the right information to the right people at the right times. Well, the CDM regulations require exactly the same thing. And that means really getting the right information to the right people at the right time, rather than what we've historically done in construction, give everything to everybody too late. For those of us who work in construction, it's fairly normal to say, okay, well, I need this answer, and somebody comes along and says, well, it's in that document that's 200 pages thick, which is really not very good communication. And I do keep on asking designers, why do they keep on producing thick specifications that nobody's going to read? And I am totally of the view that the likelihood of somebody reading something is inversely proportional to its thickness. And if BIM can give us accurate information in a much easier way than having to read all this, what is essentially rubbish, before we get to the little nugget of good things that we actually need to know, it's got to be a good idea. And I'm thinking it from a health and safety perspective, but I think it applies across the board, whatever we're actually doing on a project. CDM 2015 came into force very nearly a year ago now. There is a set of guidance. If you've really got nothing else better to do, You can have a read of that. It's not exactly the most exciting read in the world, but I'm sure you're all excited about health and safety anyway. It applies to any work on a structure, and structure is defined within the regulations, and includes some things that maybe we wouldn't previously have considered to be structures, such as pipes and cables are defined as structures, and that includes all sorts of pipe and all sorts of cable, including telecom cables and IT cables. And also fixed plant is defined as a structure. So if an element of plant is secured to something else by any means whatsoever, it is also a structure. So that's the first definition that we need to look at to see whether the CDM applies to the work. The second definition is whether it's construction. And construction has a very long definition, but just to summarise it, it isn't just construction. It is also maintenance, repair, testing, commissioning, and even eventual demolition and dismantling. So there is actually very little that we actually do to a structure that would not be classed as being construction. So just a short maintenance job on something would also be classed as construction, and CDM has to apply. And going back to the BIM, and I'm not going to go into any BIM things in any great detail, my co-speakers have done this very well already. But the summary of what BIM actually requires, I believe, are those things there. Create a common language that everybody understands, which again will be something brand new to the construction industry. Allow decisions to be data-driven, and the thing that really gels with me, and again one of the previous speakers have pitched this one as well, by a single version of the truth. And certainly I've worked on lots and lots of projects over the years, and my view is if you've got 6 different organisations involved in the project, you've effectively got 6 versions of the truth. And if we can all go to a single source of information to get the truth, we're more likely to all agree as to what that truth is. Deliver benefits using data and embracing efficient use of technology, always a good idea. I do have a slight concern about BIM, and that's if our technologists essentially steal it. Whatever we do in this process, it's got to be simple, it's got to be clear, and everybody working on the project needs to gain access to this information, whatever form it actually is. If it gets too complex, we won't use it. Okay, it can be complex behind the scenes. I don't know what goes on in these things, and I don't care what goes on in those things. As a user, it's got to be user-friendly. And bring processes, people and technology together. So we're actually all working to deliver the project on time, on budget, all these sorts of things, and I would like to add in without hurting people. Of course, BIM also has other functions that are also very useful for compliance with the CDM regulations, things like the follow-on after the construction process, the ongoing maintenance and repair of facilities is also something that CDM looks at in the form of a health and safety file and in the form of what designers have got to do under the CDM regulations. They've got to address those things and providing that information in an easily used model that everybody can know what we've actually built in, how the things can be maintained, repaired, and how often, and so on and so forth, has got to be a really good idea. Of course, if we then work on this, whatever this is, building, road, bridge, whatever it is, in the future, then if we've got an accurate model that we've been using to maintain and operate whatever this thing is, we can then bring that information and deliver it to the new project team for doing the refurbishment or the amendment or the addition or even the demolition dismantling for the future project. So using the same information over and over and over again, rather than using it once, losing it, going finding it again, losing it, and we just keep on going on like that. Building information modelling obviously requires employers' information requirements, so the employer, I know them as the client in the CDM terms, but must actually fully describe what they want. Actually, what we need to do as professionals, of course, with clients is actually then explain to them that they should actually want something else, which is what they need. And that, I would suggest, probably includes BIM. Then our team has to decide how they're going to satisfy those employers' information requirements by something called a BIM execution plan. Again, I would call that a management system. We also have information delivery tables required under the various requirements for BIM. I think we should have had those anyway, and generally speaking in projects, my experience is that we do. It may not be that clear, or even who's going to deliver it or when they're going to deliver it. If BIM makes that a little bit clearer, then that will be a good thing. And also using things like the COBE, Construction Operating Building Information Exchange, so that we have a common system for the transmission of data and where things actually are. Now, how does all that fit in with CDM? Well, there are certain things that are required under the CDM regulations. The first thing is the pre-construction information, which is a requirement on the client to provide. The pre-construction information being health and safety information related to the sites, the existing facilities, the utilities, the access, egress, any existing management systems, emergency arrangements, constraints, etc. for the site. All that information is included in the pre-construction information. It gets added to as we go through the project, including things like the results of surveys that we end up having to perform to actually find out what in reality is actually there. So that gets added to, and it is the client's responsibility. But fundamentally, it's any information that will be required by designers or contractors who are going to be bidding for the work or who have already been engaged on the project to enable them to do what they should be doing. And also to the principal designer and principal contractor, which are two appointments required under the CDM regulations. The principal designer to control the health and safety aspects of the pre-construction phase of the project, and the principal contractor to control the health and safety aspects of the construction phase of the project. And basically anything that they're going to need to manage, monitor and coordinate the work on a project. And I would suggest that the pre-construction information is fundamentally the BIM model. So the PCA provides the basis for preparation of the construction phase plan as well. The construction phase plan is the management system for the site, and also will provide some information that goes into the health and safety file, which is just the health and safety information for future use, maintenance, repair, etc. After we've actually finished the current construction project. So these things are all linked. Sorts of things that we've used in the past, that's a pre-construction information register, otherwise known as a document control system, because all the answers to the health and safety questions are in other documents. That could actually just be the BIM model. It doesn't have to be something separate. I would suggest that what we really want to try and do is not repeat things. If this information is already in the BIM model, then let's use it, rather than have something separate for the compliance with the CDM regulations. The PCI, the pre-construction information, for it to complete, must include proportionate information about the project, which would include the client's brief, employer's information requirements, key dates for the construction phase, planning and management of the project, which include the resources and time being allocated to each stage. And one of the previous speakers was talking about the the 6D and planning, etc. This could be part of this as well. Cooperation between the various duty holders so that the work is coordinated, which is also part of BIM. Health and safety hazards on the site, including design and construction hazards and how they will be addressed. I'm not sure if anybody's actually done this in the software terms of BIM, but one of my hopes is that we can actually have a 3D, 4D model that identifies the significant hazards that exist on the site or within a structure that we can easily get information on straight from the BIM model, rather than just have this list of things that don't really tell us what we're actually going to be dealing with or how we're actually going to deal with them. And any information relating to any existing health and safety file, and if we've actually got an established BIM model or building information model, then fundamentally that's going to be the health and safety file. Other things that BIM's going to do for us, hopefully, is help us deal with design interfaces, because that is a perennial problem on most construction projects, because there's lots of different organisations involved. They're only fundamentally interested in their bit of the design, and anything else that anybody else decides that it might not fit in, they always think it's the other designer who's got to change things. We need to make sure that we do properly control these design interfaces. This is what we have used on previous projects. We call it, it's actually the minutes of the meeting for a design interface meeting, and we identify what the problem is, who's going to do, or what we're going to do about it, who's going to do it, when they're going to do it, and whether they have actually done it. And again, I do get a little bit frustrated with other systems that we perennially have in construction, like minutes of meetings that nobody ever reads, or at least if they do, it's at the next meeting, and all the actions that were actually identified have not been done because we didn't read the minutes until we get to the next meeting. And I would suggest that can also be incorporated into the BIM system. It's about management. And of course, somebody else mentioned it, clash detection. I have worked on projects with 3D models. Clash detection is fantastic. Unfortunately, it doesn't actually tell you what to do about it. But at least it does tell us we have a problem. And it does work. I mean, sometimes there are some problems with the software, and sometimes it doesn't pick them all up, which we found when we actually constructed it. But the vast majority of them have been picked up, and we're able to design the issues out before we ever ordered the material, before it ever turned up on site, before we had to rework it. And I think there is still a tendency, it's getting better, but there is still a tendency in construction to construct everything twice. We construct it the first time, find it doesn't work, and then construct it again. It's better than 3 times, which used to be how we did it. Designers have specific duties under the CDM regulations about assessing or addressing all the risks associated with their designs. There is certain legal obligations on them to provide information. Lots of systems for actually doing that. They're just 2 options. Again, we can incorporate that into the BIM system. Construction phase plans. The principal contractor's responsibility, which is the management system for the site. Got to contain health and safety arrangements for the site rules, specific arrangements for dealing with particular risks. That can all be built into the BIM model, and the principal contractor can actually plan the work using the BIM model and decide how things like the temporary works are going to be installed and the sequence of events that can be done to actually deliver this project in an effective and safe way. The existing construction phase plans are quite voluminous. We definitely don't need to do that. In fact, what we actually see up there is a one-page health and safety plan. It's only for a short job. Yeah? If we were talking about building a building, it would probably need a bit more than that. But not overly complex, site-specific, etc. Again, we can utilise the model to complete most of this, and as all the contractors will have access to it, they'll be able to all see it. Health and safety file contains information that's going to be useful to people working on this thing in the future. It covers lots of things. If you want to have a look at the detail of it, then go and have a read of that document I mentioned before about the guidance document. If you're interested, its number is L153. Basically includes information that will be useful, and that should be the parameter under CDM for including anything in any of the documentation that is produced for CDM. Will it be useful? I would suggest that should also be the parameter for including anything in building information modelling. Will it be useful? If it will, include it. If it won't, don't bother. And if you have any questions about any of that, or anything else regarding health and safety and how building can be related, come and have a chat to me over lunch. Thank you.
In terms of BIM used for health and safety and CDM perspective, after saying its importance from an energy perspective as well for new and existing constructions. And now before lunch, now we are going to have one more presentation from Evan from London Rock. He's going to give us a presentation about some projects they are doing. Scan to BIM, he's going to give us and demonstrate some of their project, how actually they produce BIM model, from the laser scan data. Yeah.
Afternoon. Apologies, I'm not as organised as usual. Yes, it's fine. I have a few videos, that's why I just switched from, I'll be alternating between the PowerPoint presentation and the videos. I work, let's go back to that. Sorry, we need to find that presentation. Yeah, this is I'm wearing a few hats today. I work for London Rock. I'm a digital engineer, and I work within the workmanning department. I've got a civil engineering background and construction mainly for the last 20 years. And a few years ago I started a track and I started studying and then I landed in BIM. From there, my academical interest took over, and I'm a former student of Dr. Arici. So I'm interested in linear algebra, data mining, machine learning, and recently coding involving Python. my view is to give you a quick tour of what is happening within the BIM industry to convert 3D data, and I specifically say 3D data and not scan data, because there's a number of ways of finding and creating 3D data. So I'm going to start at the end, work my way to the middle, and then continue from the beginning until I reach the middle again. When we have a model, a BIM model, we hope to extract information of it. We input data, and we want it to tell us something. So, in a way, it's explicit. It gives back exactly what we put in. When we use scan data, 3D data, we hope to extract information from it. But the data we have is implicit. It's not explicit. So what I mean by that is you can take a look at the point cloud. Maybe I should try and open that now. Yeah. So this is a point cloud that I've animated or just flown through of Waterloo Station in London. Looking at it, I'm saying all you see there is coordinates with a value to it, a few scalars, and nothing more. But we have the ability with our wonderful brain power to recognize things. And there's a lot of information that we can deduct from that. So the research that I'm busy doing the last year looks at extracting this kind of information, implicit data, and converting it into information or explicit information, explicit data. So this was just an illustration. There are a few more point clouds, so it's clear that we've got a huge potential of data that we're not tapping into. So I'll carry on. This is still Waterloo Station, so this is all just coordinates in a spreadsheet, essentially. But that's not what we see, and what we're trying to get to is to have these coordinates in a spreadsheet tell us more than just the length of the wall or the position of the window. So the basic format for scan data, 3D data, is usually in either ASCII or binary. I'm not going to bore you too much with techie stuff. But there are a few things happening within this environment. Big increases in productivity from automatic registration, so point clouds or 3D data can be viewed within the nesting and within its the coordinates that involve the 3D environment. Usually the surveying department would take care of that, but it is very helpful to be able to use any given scan within a quickly attainable nesting, I'll say the word again. So that's one of the interesting things that's happening at the moment. And, well, it's not. So what do we use point clouds for? What do we use data, scan data at the moment? Usually it's only for looking at things. It's for animation, for showing the client something, and at a minor scale for getting dimensions to model on. Software available on the market does comparison, does sectioning, does voxelization to get the cloud into a more manageable size. but really we're not using a tenth of the potential that we can. So why do we want to automate the process of creating a BIM from scan data? There are a few easy wins. Design flow, design workflow improvement, enhancement of the management of the environment, and uncertainty in bidding. This is all good if you can easily do that, but it's not as easy as it sounds. To create a BIM from scan data is a lengthy process and it's error prone. We rely on the modeler to give us his interpretation of the data, and that is not consistent. So the amount of error that we need to deal with is not acceptable. So we need to find a constant in this process, and to do that, the only way I could see was to use a mathematical system or an algorithm. There are a few things happening in the industry at the moment. There are software packages available that claim to help us in this process. I've had a look at a few, and it's not really there where I think we can safely say it's going to change the game. Let's fall back, sorry, I'm getting ahead of myself. If we look at manual creation of modeling, I've recently used a data set of 1 terabyte of raw data. This was in BTS format. It took me 6 terabytes to process this. So it's a very heavy, memory-heavy process that requires a lot of computing power and a lot of time. A lot of dead time in the process because we sit and we wait for the program to assess the data and to load it into the format that we want to. Quite frustrating, to be honest. The model needs to be, or the data needs to be registered. Like I said again, it needs to be cleaned up. For relevance, because we don't necessarily want people in there. We don't necessarily want moving objects. Then we manually segment the data, so we break it up in usable chunks so that we can only use the data, the areas that we need to. That makes it easier to handle for the program, for the hardware that we're using. We attach snap points or hotspots to it, and then we basically trace. We say, I can see a wall, so I would like to insert the wall into the data, and it's a tracing exercise, which is not, especially when you're dealing with irregular surfaces or shapes, it's very difficult to do, and you need a high level of skill, and quite inaccurate. So let's keep over that because I think I've said enough about manual creation. Looking at automated technologies, we've got people with Autodesk here. I've looked at Point Sense. You can see there's a few on the screen there, like the CloudWorks. Very bespoke, usually very specific to certain shapes and like pipe or diameters that are known. In essence, what it's doing, it's comparing, but it's the shape that it's been told to shapes within the data, but you have to be very specific with where it needs to look. And it does it in a 3D environment, which makes it slow. Recent developments have been looking, or researchers have been looking at making this process a bit more efficient. So algorithms that's been developed has been the subject of my recent dissertation. So there are a few areas that's been identified. Looking at polygonal meshes, which brings within the model. It changes the structure of the data from being pure geometry, in other words, just coordinates, into surfaces, vertices, best fitting planes, and then the big one, detection of planar patches. I've done a few case studies. I've looked at a few case studies, 4 to be precise, and compared them with what I thought is the relevant criteria. The end result was the process that's used at the minute is using planar patches or region growing to extract surfaces, flat surfaces from a model. These surfaces are then expanded until they cross each other, and from that the wireframe is constructed. This is very simplistic, there's a bit more to it than that, but all of this happens within a 3D environment, and all of the data needs to be interrogated again and again and again. This is very slow and it scales very badly. In other words, to get the algorithm to work, the settings for it needs to take into consideration the size of the data, and also how close the points were scanned to each other, so the resolution of it. Once you've got that, you have a certain window in which you can detect planar patches. If you go beyond that window, you will get over-segmentation. In other words, a flat wall might come out as 3 or 4 different patches, and that's not what you want. Or you might lose smaller detail. So after a lot of thought, I just realized that we beating around the bush actually about dealing within a 3D environment constantly. So for the last 6 months, I've been coding to try and scale this back to the second dimension. So we work in the 2-dimensional environment where simple regression is used to detect straight lines. So if we take a section through this building and we cut it in a thin slice and look at it from a normal perspective, so orthogonal, you will see a line where the floor is, and you'll see a line where the walls are. When we then repeat the process and take a parallel section, this will be repeated. If we record the nodal points, and we do that again and again and again, we iterate it until we run out of geometry, these nodal points will form the corner of where the wall and the floor meets. Or if we scale it up, if we're looking at a corner section, you will find irregularities within the lines that can easily be detected by simple regression. So we look at a very small part of the data at a time, and we form a vector model by then identifying nodal points and line the nesting of lines within the nodal point. So this was a bit scattered, but let me see if I can do something. This is a quick demonstration of what the algorithm is doing. As you can see, I've taken the chimney base, vertical and horizontal sections were taken, and then the sections were looked at in isolation, and regression told me there were certain straight lines within a certain parameter. These lines were then put in context. The nodal points were recorded, and then as a bit of an add-on later on, it was voxelized or put in a cell, and then it can be taken further. So that's a very short description of creating geometry, but that's not where it ends. We don't only need geometry, we need this geometry to be infused with semantic information. And this is where the previous speakers have kept getting back to, and this is the important part, and this is where I hope to take things further, where the knowledgeable people, so the stonemasons, the bricklayers, the people who know the material, need to now come. And once we've got a virtual DNA for a chimney breast, we can now implant this with parametric information. I'm quite interested in machine learning, and if you take clustering algorithms, if we do the next scan and it picks up a chimney breast, we can now associate the information that we've implanted in this virtual DNA, and we can then add it to the database, which means if we have more of these DNA sequences, as I call it, we eventually will have a big database with parametric information, and then the association between elements can be further examined, where at the moment we only have what is implanted in the model at the design stage. So apologies for me not speaking too well. This is it's a bit new and a bit daunting to me, but this is essentially what Dr. Yusuf and I have been busy with, and hopefully you find this interesting within the short time that I had to explain it to you. Thank you.